I think we'll go ahead with the program, and I've really been looking forward to this. Maybe I can get some more people coming in. So, Don, do you want to do the introduction?
Okay, well, tonight we're fortunate to have George Srdanov with us, and he's going to talk about deep space astrophotography, setup, data gathering, and processing. And George is an IT professional and avid astrophotographer. He lives in Knoxville, and he sometimes goes to takes images from his backyard, Norris Dam State Park, Foothills Parkway, or the Tom K. Allen Observatory. And I know I've talked several times back when we actually went to Tom K. Allen. I've gotten tips from him a few times out there and found he was quite knowledgeable about astrophotography. So I thought it would be good if we could have a more lengthy discussion of it tonight. And so he's going to talk about the different phases of astrophotography, going from technology basics through equipment setup, data gathering, and stacking and post-processing. So with that, I'll turn it over to George and let him take over.
Hi, everybody. So I'm very glad to see you. Thank you for the introduction, Don. Right now, I'm actually using my phone just to get the introduction, and I'm going to switch over to my other PC, and I'm going to stop the video. So let me just quickly hop over to the other machine, and then I'm going to start sharing the screen there. All right, hope this is going to work out. So we'll see. I have this little button. I can actually annotate things in case we need it. So that's going to help us. So, all right, let's get started. So I actually have created a bunch of screenshots here. So we have about 50 slides to cover. I'm going to pass through most of them rather quickly because they are just kind of more reminders for me. If weather permits, sorry, not weather, but sorry, my bad, time permits, we can actually jump into some examples that I have, kind of prepared some stuff. So I'm going to do a little cheaty here, and then we'll go from there. All right, so I started, very modestly with a small Celestron Tyroscope. The mount was very flimsy. My first camera was probably like everybody else's, my cell phone. Since then, I have upgraded the equipment. I got a nice 6-inch Magnetonian scope. Now I also have a mid 8-inch SCT, which I kind of use it, but not that much as the Mac one, the Magnetonian. That's kind of my go-to scope. I upgraded my mount from an Explorer Scientifics XOS2 to an EQ6 Pro. Works really nicely. And thanks to COVID, and we had to cancel our vacation this year. So, 2020 vacation was gone. So I got permission to spend my plane ticket on cameras, astronomy cameras. So yeah, I got 183 mono and 183 color on a very good deal. So now I'm, dipping my toes more and more into mono imaging. Of course, hopefully by Christmas 2021, narrowband filter is going to somehow, appear in my front yard, or Santa is going to drop it off. We'll see. But, be ready for more clouds. A few pictures here, you probably have seen them. Most of them are the same old ones that I had before. I added one that we are going to look into a little bit more deeply. So this is my first actually mono imaged object, M27, the Dumbbell Nebula. So this is where I was, practicing the mono imaging and stacking and processing. So I'm going to share my experience with that. Before we go there, we have basically what I want to do here is just kind of do a quick recap with, astrophotography is a very wide area, of, this hobby. You can do just simply a camera with a lens and do wide field. You can do planetary imaging. Tonight, I'm going to focus on the deep sky objects. And as we know, the deep sky objects, they are dim objects. They are pretty big ones. They are kind of static in a sense that they are not rotating like Jupiter, for example. You know, when you look at Jupiter and you take shots, they actually, you know, definitely you can see it through time that the images are kind of getting blurred if you don't do the rotation and things like that. For deep sky imaging, because the objects are dim, usually a faster scope is better, and definite long exposures are kind of mandatory. So in a sense, long exposures, like, you know, multiple seconds or multiple hundreds of seconds versus, you know, if you do just planetary, you would, you know, do a sub-second exposure. With that said, when it comes to long exposures, tracking is pretty much mandatory and guiding is highly preferred. And we'll touch base a little bit later. I have a slide on that, so we're gonna kind of dig into it a little bit deeper. For regarding the telescopes in general, you know, you have the reflectors, you have the refractors, you have the Cassegrains. So which scope you will pick, it actually depends on the object itself, but, you know, pretty much all of them will work, you know, good. Just to kind of mention, there are kind of specialized telescopes called astrographs that are actually optimized for astrophotography. They are not so good for optical, so visual observing, but, you know, they are actually highly optimized for imaging. In addition to the three first mentioned scope, you have the hyperstar type of telescopes, which is basically if you would plug a camera instead of here, instead of putting the camera here, you would put it up here at the front. That's the hyperstar. The good thing about the hyperstar is that you can actually have an object, a telescope that can have three purposes. One is just a standard SCT. The second one would be an SCT with a focal reducer. Then you can use it also with imaging both ways. And the extra special design would be the Celestron Rohn Ackermann Schmidt design, which is fully optimized for imaging. With Hyperstar and these RASA scopes, the crazy things about them is how fast they are, in a sense that they are like sub f2 speed. So whatever the normal people do with, you know, f6 or f5 telescopes in minutes, these guys do it in seconds. So your exposure, you know, would be a lot lower time because they're just so much faster. When it comes to mounts, we all know that there are different types of mounts: Dobsonian, alt azimuth, fork. You know, you can have like something like a star tracker for, you know, wide field imaging, and the preferred one for imaging is basically the equatorial. Why the equatorial? Because as I mentioned, we need the tracking, right? And you want to track as steadily as you can with the smallest amount of vibration. You want to basically counter Earth's rotational speed. That said, when it comes to tracking and guiding, you always have to do a proper polar alignment to avoid the errors or minimize the errors as much as you can. So you can do just a standard setup with the polar scope, or you can have a little bit more specialized setup like a Polemaster camera. I have this one. You know, I love it. It just, you know, takes me a minute or two to get it you know, where I wanted it. But unfortunately, there are some times where the Polaris is not as good, you know, location, because there are some trees and things like that. And that's where, you know, some alternatives can be used to actually align your setup. So I'm going to just kind of quickly go back a slide or two just to mention this. Some of the software that we use these days, they are using the plate solving technology to actually figure out where things are. And I'll get back to this in a second, but basically what they do is they take a picture, they figure they out where the telescope is pointed, and they go into a different place and they take another picture and they figure it out again. So one of these software is called ASTAP, and we're going to play with it in a little bit later. But for now, let me just kind of go back to this slide where we talk about the drift alignment. So when I do my polar alignment with the PoleMaster camera, that brings me down to probably a few arc minutes of error in the alignment. But when I really want to have a really good, nice guiding, then I usually go with the drift alignment. The problem with the drift alignment is that it's actually taking quite a bit of time. Each cycle, when I do the drift alignment, it basically takes me between 5 to 10 minutes. So every adjustment I make to the scope, I need to wait 5 to 10 minutes to do the next adjustment. Of course, in time and practice, that becomes pretty quick, and you can get it done in about 30 minutes. But it still, takes time. So basically what you do here with the polar alignment, because you don't need to use Polaris, you point your scope to east and west, and then you adjust the altitude. You adjust how high you need to point the telescope, basically from north onwards towards south and back. And then you point towards the telescope towards south, basically towards the meridian and the equator intersection, and then you actually adjust your mount left and right. So this gives you a little graph here, and I basically made here a little reminder for myself. First of all, it's very, very critical to be patient. If you are rushing through things, then it's going to really just kind of make your life harder, because sometimes due to the sky conditions, the error is going to be big and it's not going to be averaged over a good amount of time. So if you jump on it quickly, it might actually mislead you. So what I do, I kick off one drift alignment cycle and walk away, literally come back 5 minutes later, set up a timer on my phone, and then I look at the graph and then adjust as needed. So as I mentioned, if your alignment star is on the east or west horizon, you need to adjust your polar axis up and down. If your alignment star is at the meridian and equator intersection, you need to adjust the polar axis left and right. So back to this plate solving software. The reason why I'm actually mentioning this whole plate solving technology is actually a tool that is used in SharpCap, as well as some other softwares which are helping you to do the polar alignment properly. One of these software is called N.I.N.A, Nighttime Imaging and Astronomy. And it has a really nice plate solver-based polar alignment. It does not need Polaris. It goes, as I mentioned, like the drift alignment principle. It goes, takes images on the east and west, or west, I'm sorry. And then you can do the same with south. And the trick is that this software, basically, when it measures either of the errors, what it does, it goes to one side, wherever you tell it to go, then takes an image, then moves on that axis a certain amount, let's say a degree or degree and a half. I think there's a measurement, there's a variable that you can set. And once it goes to that location, it actually takes another picture and compares, is my position where it's supposed to be? If there is any error in the polar alignment, it's going to tell you, hey, you are X amount, X arc minutes or X arc seconds away from the ideal position. So you're too much east, too much west, too high, too low. It's going to actually write out the number. So what you need to do is you would click on measure altitude error, and it would actually write out in a little message somewhere just below and say, hey, this is your error that you need to do. You would do an adjustment and you repeat the error. The good thing about this is each cycle takes about 30 seconds. So I can actually do a lot of iterations with a very short period of time. So usually with this, I can set up my polar alignment within minutes, up to, let's say, 10 minutes. I can make probably everything up and running, and I can be ready to roll. This option here that it talks about DARF slew, what it does, it's actually going to move the telescope into one direction with RA axis and then slew back. And if the alignment is actually good, then when you take this exposure with the camera through the slewing, you're going to see actually a line. And it actually says here in the instruction, it's a very simple way to check your alignment. It actually works really nicely. I use it very often, but even when I'm done with this, I still go back and do one cycle with my drift alignment and make sure that everything is perfectly there. What I measured the last couple of times where I was playing with this and using it, I was able to get down to sub arc second error. So get like 0.5 arc second error when it comes to guiding. So let's just go to the next slide. So tracking and guiding, right? The tracking is just a simple rotation of the telescope. We need it to counter Earth's rotation. The guiding is a little bit more complex, and it actually has an active feedback. So there are multiple ways to set this up. The simplest one is you attach a secondary scope and a secondary camera, and it basically, while the main camera is imaging, the guide scope is taking short exposures, maybe 2-3 seconds, and it's comparing the location of the monitored star. And with if there's any error or any movement in the star location, it's going to counter it by sending active correction pulses to the mountain, keeping your target where it needs to be. One of the softwares that actually I'm using, and it's actually a free software, it's fairly easy to use, it takes a little bit of a training, it's called PhD tool, which means push here dummy. And I completely agree with this. It's really simple and easy to use. It takes a little bit of setup and a little bit of watching some videos, but once you get it going, it's literally just push here on this, guiding button, and it works. And as I mentioned, my error is typically between ±1 arc second. And this is a typical Tennessee sky. Luckily, occasionally, like very rarely, but we occasionally get a really, really nice and calm night. And in that case, you can see that the guiding is compared to the previous one where you had the whole circle here, right, everywhere. If I go and do the other one, you can see that it's actually very, very nice and tight. So it's just on one axis is slightly elongated, but it's actually very nice, and the graph is much cleaner than the other one. Now, a new version of this software, the 269 development version, actually has a new feature called multi-star guiding. What it does is basically, if you look into this picture, right, you see multiple stars, but I'm still only monitoring one star. What the multi-star guiding is doing, it's actually picks multiple, I think like 5-6 very strong signals, and it actually goes and monitors all of them and calculates the error rate on all of them. And I think it averages out, or there's an algorithm that actually cancels out just the turbulence in the air. And what I noticed, and I think Ricky also noticed the same thing, is that it actually drastically reduces the wibble wobble of the graph. So we measured about 50 to 40% better, guiding performance over a single night. Very simple, just one click, no extra setup needed, but it's actually very helpful.
Do you let it pick the stars when you do that, or do you have to pick them manually, or how does it?
So when you do the multi-star guiding, it actually the system does it on its own.
Okay.
I try to click on multiple stars, it doesn't let me do it, so you just go with it, and it actually does a pretty good job on this one. Any more questions here? Okay, so another thing that I noticed, and it actually helps, it's and I'm using it actively, is a periodic error correction. So what is the periodic error correction? The periodic error correction basically is the how should I say this, a property of the worm gear that's built in your mount. So the periodic error is basically the imperfection caused by the manufacturing process that has, very small error rate. It's probably down into, microns or tens of microns. But when you do the long exposures, right, with high focal length, those microns actually get, more and more, it gets multiplied. So what you can do is you can actually record this periodic error, and you can send it to your software, your mount controller software, or you can actually burn it into your hand controller. And when you do that, what happens is, instead of relying on the error to occur and then the guiding to counter it, the mount actually knows, hey, I have this slope coming up. Let me speed up a little bit or slow down a little bit to keep my position more uniform. And that makes the guiding part then much easier. So in combination with the guiding, this PEC correction actually keeps it, really nice and smooth guiding graph. And don't get really bogged down because of the graph is, noisy and spiky. The critical thing to always look for is, how is my image? How is my long exposure? If it's good, don't worry about the guiding too much. But what I'm saying is that all of these things can help drastically improve the performance of all of the imaging. Another critical thing to deal with is basically the focusing. I have spent quite a bit of time trying to eyeball the focus, on my camera, and it was no fun. I look through the screen of the camera, through the eye finder, and everything looks okay. And then when I download and I start processing, I see, oh, well, it's not really that perfectly focused. It's close enough, but you could do better. Then I discovered this Batino mask, and it's actually a really helpful utility. The point is that these slots that are on this mask under angle, they are producing basically a star shaped diffraction, pattern. And if everything is in focus, then you're going to get like a perfect little, star. If it's off focus, then you're going to get like a line that's not really going through the middle. It's very easy to notice it, in some of the software actually knows how to deal with it. Another thing that actually I have found so recently is something called a tri-Batino mask. If you look at the mask, this is actually how it looks like. I found it in the Cloudy Nights forum. People were talking about. Here's a link that can actually take you there to, you put in some metrics, and it's going to give you a shape that you can actually print out, cut out, and make. So what I did is actually, I went through the process, and for my telescope, I did the math, printed it out, did a 3D model, and then I 3D printed it from plastic. It's a very similar mask like this. And if you take a look, compared to the previous slide, right, you have these slots, just like you have like 3 lines, like 1, 2, and 3, right? If I, this color is not really visible. Let me kind of make it red. So here's one slot, here's another one, and here's the third one, right? And with these 3, you have these kind of 3 spikes. However, the actual pattern of this star was very dependent on how and what angle is the position. So how it is positioned on the telescope and under which angle. So this tri-Batino mask, if you take a look, it's actually nothing special. It's actually like the same mask that we had prior, but it's 3 of them combined into 1, right? So you have still the 3 slot approach, right? But you have them rotated under 120 degrees. And you get this kind of pattern, a much more complex pattern. But the good thing about that one is that you are going to notice, if you have, let's say, a Newtonian telescope and not so perfectly collimated, one of these spikes is not going to be in the middle. If everything is perfectly aligned and all of these spikes come out in the middle, then your collimation is really nice. I know that, you know, many times I just kind of go there, I look at the picture and I see, okay, this is not good. Go do the collimation again. Very helpful utility, and it's easily, you can get it done. You can make one very quickly. You know, if you have access to 3D printer, you go on that link, you type in the size of the telescope, the central obstruction, couple of parameters, and it's going to draw out a pattern that you can download, and then you can print it out and do whatever you want to do with it. Okay, so let's see, what's the next slide? So, okay, so we went through this basic phase of just, you know, that you can use it for visual observing also. Any questions so far?
Do you know, I recently did the periodic error correction on my scope, and it helps the guiding a lot. Do you know if you have to redo that occasionally, or is it pretty much
Unless you,
for a while, or?
So there are two things, a couple of things to pay attention to. So the first thing is, if you take apart your scope, your mount, and you don't put the gears exactly the same way, you definitely want to rerun the PEC curve, you know, and teach it again. The second one is, it depends where you keep the PEC curve. Are you keeping it in the software, or if you keep it in the hand controller? But you have to park the scope every time. Otherwise, you will have to re-record the curve, because there could be a phase shift, right? So if you turn off the mount just at the whatever position is, where's your starting point, right? It's not back to the park position, so it's going to start applying the curve from the position that you left it off, and that's not what you want. You always want to apply the curve the way you recorded it, right? Otherwise, it's not going to be matching. So there's a phase drift. Some softwares, they have an ability to deal with the phase drift, but usually it's such a pain in the neck, it's not worth it. So I was actually watching a video earlier today. The guy was showing how to do the permanent periodic correction in the hand controller with the EQ6 mount. So I'm going to try that next time. But yeah, you want to make sure that you park, and only if you mess with certain things and you don't park, then you have to re-record it. Okay, any more questions? Okay, let's start playing with digital cameras. So the basic of the digital camera is a sensor, right? And most of the sensors, they basically are formed with photosensitive elements. So each of these little squares is just literally a photosensitive element. It's a phototransistor, if I remember correctly. By the nature of the beast, you know, these photosensitive elements are not really color sensitive, they just light sensitive, right? And how we make them color sensitive is we put a color matrix, which is called a Bayer matrix, and group 4 of these photosensitive elements into 1 pixel. So this is basically the simplest way how to make a color camera. The problem is that, as you can see on this little ducky, it's a very good example. With this kind of approach, right? And if you don't have enough pixels, your picture is not going to be really nice when you use the raw format. So we do something called debayering and binning. And basically those are the operations that deal with these kind of problems. So what the system does when you do a one-shot color camera imaging, it tries to figure out all of these extra missing pixels. So if you look at the pictures on the raw, what the raw data has, right? For red color, you have only 4 pixels of red information, but you have to figure out 16. So you actually have to you know, user imagination or an algorithm to figure out 75% of your data. With the green, it's a little bit better situation because every other pixel is green. So you still have to figure out 50% of the data. So it's a lot of guessing work. It's interpolation algorithm. When it comes to the mono cameras, we have a different approach. You use the photo sensor as is. So this area here, I'm jumping back and forth. So this area, these red, blue, and green pixels, they are not there. It's just gray. And what happens is you actually put the individual filters in front of the sensor, and then you take a black and white picture through that filter, and you figure out for that color how the picture is supposed to look like. It's a good news, bad news situation. The good news is that the image quality is higher because you just have 100% of the data for each color. The bad news situation is that you have to do every single shot 3 or more times, right? For each color, you need to take a black and white image. And then the bad news is that you have to deal with a lot more data and processing becomes a little bit more complex. So yeah, another part of these digital cameras, sorry, the sensors, is what kind of technology they use. So I put out here a couple of terms that people are using, and just to clarify them. So what are the FSI and the BSI sensors in the cameras? So the front side FSI is basically means front illuminated sensor, front side illumination, and the BSI means backside illumination. So what does that mean? As we mentioned, these sensors is just a matrix of photosensitive elements, right? And these photosensitive elements needs to be tied together somehow to the rest of the electronics in your camera and then to your laptop. So there's some wiring involved in there. In the front side illumination cameras, how they used it in the past, and what's I think a more simpler way for manufacturing basically is using the metal wiring to be in front of the photosensitive area, which is okay, but it's not as great. So when Sony started making first, I think I might be wrong, but I seen Sony making the first backside illuminated cameras, which is basically keeping the visible area, right, unobstructed by the wiring, the metal wiring. So you don't have any reflection from the metal wiring, and they have increased the sensitivity of the sensor, aka the quantum efficiency. I have seen it increase it, by 30-40%, which is significant, saving in your imaging time. Because if your camera is, let's say, 60%, has a 60% quantum efficiency, versus a camera that's about 90%, in the newer sensor, they are mostly about 90%. Then that means that there is about 30% reduction of imaging time for the same quality of the data. So since I mentioned the quantum efficiency, let's just clarify what that is. So the quantum efficiency is basically in the digital camera is a measurement of generating electronic impulses based on the light captured by the sensor. So it's basically a transformation of photons into electrons. And basically, the higher the quantum efficiency is, the better the camera is. It's more sensitive, quote unquote. What does that mean for us? Is basically, let's just put it into a practical example. If a sensor, the photosensitive element, gets hit by 100 photons, if the quantum efficiency is 60%, that means that out of the 100 photons, there's a chance that there is going to be 60 electrons generated. If the quantum efficiency is 80%, there is a chance that there's going to be 80 photons from the same 100. So the signal is going to be just simply stronger. When it comes to the amount of these electrons generated, there's another term that we need to clarify, and that's called a full well capacity. So what does that mean in practical life? Imagine the full well capacity as being just a simple bucket of water. And the electrons being generated by the photons are being drops of the water, right? So I have 100 drops of the water. The quantum efficiency says that out of the 100 drops of water in the bucket, I'm going to probably have between 60 and 80. That's usable for me to transfer it further. So the full well capacity in this particular case, in the analogy of the bucket, would be how big is that bucket? How many electrons or how many drops of water I can keep in my bucket before I have to actually empty that bucket and potentially lose some of the information, because I'm dealing with emptying the bucket, right? And if the water keeps dripping in the same place, if I remove the bucket because I need to empty it, right, that information is lost. Any questions on this one?
George, I have a question. Just before you go away from this one, it's very interesting that you show the relative quantum efficiency of the different sensors, the blue, green, and red. It's really curious that they seem to correlate strongly over in the infrared. So if that's the case, we have a way of actually comparing the quantum efficiency of the different sensors, normalizing. Do they really correlate that strongly out in the infrared?
I don't know about that one. I was just basically looking at the visual range, but I think what happens is that, so these kind of three lights, if I kind of do the real interpolation, this is how the graph actually should be looking at, right? So this is basically the sensitivity of my imaging mono sensor before I use the filter, right? And this particular graph is about a color camera, and it talks about the quantum efficiency. And you're going to see it in a marketing material. Oh, we have like 95% quantum efficiency. Yes, but at which point on your graph, for which wavelength? It's actually for the green one. That's kind of the higher one. So why is this important? If I'm imaging with my, let's say if I'm doing a mono camera, or I'm just, even if I do a one-shot color camera, you're going to see that your images are very often dominated by the green color. It has a problem with when it comes to the light pollution, but just the fact that the red filter and the blue filter have less elements in the whole Bayer matrix, it just gives you more information on the green. In addition, that the the efficiency of the sensor is the highest in the green range. So that's why I was actually using this graph. But to your point, I think that the underlying black and white sensor, no matter what it happens, at certain point, it just starts losing its efficiency. I know that there are some sensors that are actually optimized for the 700 nanometer or higher wavelength. So they are specially optimized for infrared imaging. But this particular graph and this correlation is for a standard, photo sensor in a color camera. Hope that answers your question.
It does. Thank you so much. And I realized something that so much depends on the filter and the filters used. So that's very good. Thank you, George.
Mm-hmm. Okay, so a couple of more things to talk about, and then we can move on this slide. So in addition to the full well capacity, the quantum efficiency, which as I mentioned, think about this bucket and the capacity of the bucket. The dark current in the analogy of the bucket, I would say it's how clean is my bucket? How good of a chances are that my bucket is kind of a little bit rusty and some contamination is going to leak into my water. The thermal noise also kind of plays into that. Also, how good the quality of the signal is going to be when I read it out, and that's where the cooling comes in. And think about the read noise is basically, in the analogy of the bucket, would be how clean is the pipe between my bucket and wherever I'm transferring the water. These are all these some characteristics of the sensor that we have different ways to deal with. And there's another thing that we kind of need to deal with is something called an M glow, and I'm going to just show you how that looks like and what does that actually mean. So when it comes to the sensor amp glow, some of the CMOS sensors that we use these days in the cameras, and this shot is from 183 Sony's 183 series of sensors. They have this kind of star shape that shows up in the pictures. Some other sensors, they actually have a different shape that's going to be visible. Some will have in the corners, in the edges, and so on. This is basically, let me just kind of quickly scroll back to this sensor. These additional parts of the sensor, they're heating up. And those additional parts are the ones that actually generating that kind of extra contamination of our signal. So to deal with them, you use cooling. The lower you get the temperature of the sensor, the lower that current is, the dark current, the noise that is being generated by that extra electronics around the photosensitive area. You can add a fan by yourself on a camera, and I have seen that, and people actually put also a Peltier element in between the cooler and keep the camera actually cooler than would normally be below the ambient temperature. However, doing this, and I was actually playing with this some time ago, and then they decided it's just not worth it. The problem is that these standard cameras, which were not meant to be cooled, they don't have a thermally isolated chamber. So what can that cause as a problem is that you can get humidity into the area where the sensor is, because it's just not filtered out, not sealed out. So that's why I would actually recommend to use a proper thermal element, Peltier element cooled camera. And basically what happens is, as you see here, you have the sensor, and behind the sensor, so this sensor actually has a front glass, and it's a separate chamber, and it has this access point to put a desiccant pill inside to keep the moisture out from the sensor. And somewhere behind the sensor, there's a Peltier element, and through these little notches, there's a fan that cools the Peltier element. So you can get down the sensor temperature below, probably 30 Celsius below ambient temperature. That actually keeps the noise and that star shape, that amp glow in check pretty nicely.
I have a quick question.
Sure.
I don't know if you saw it, but I have an image of the Rosette Nebula in hydrogen alpha, and I've got something that I thought was amp glow. I'm not sure. I think Don thought it was due to something else, and it was a fairly long exposure, like 30 minutes. And I think I heard somewhere that the read speed from your camera affects the amp glow. And I have old USB connections that are USB 2 instead of 3. So does that make any difference?
That could also make a difference. But I don't think that should make that big of a problem. Depending on the camera itself, it might be or may not be. Most of these cameras these days have a local DRAM memory cache. So it could be, I don't know the exact specific case, but for example, 183 has 128, the QHY has 128 megabyte cache, but your image, when you read out the sensor itself, right, it's about 20 megabyte. It's a 20 megapixel. So it's about 20 megabyte or maybe a little bit more, but it still fits a couple of images into that DRAM area. So if your camera has a DRAM cache, I don't think it should affect you, but I'm not excluding. But if the camera is optimized for USB 3, I would highly recommend doing it. I had some problems before I realized that my cable that I was using was not rated. So I had a cable that was a USB 3, but because I had a USB-C connector on the laptop, I figured I used a little adapter, had a little extension cord that would go from a standard USB to a USB-C connector, and that part was not rated for USB 3 speeds. So for quite a bit of time, I could not figure out why is the system constantly reporting that I'm actually not using the USB 3 speed until I found out that that little adapter was not rated. The second I plugged everything into directly a USB 3 rated port, everything worked out just fine. So if you have an option to use a USB 3 port with the USB 3 camera, I would highly recommend doing so. But I don't know, without actually looking at it and knowing the exact camera model and things like that, I can't tell, was it the AmGlow or something else.
Okay, I'll send you that information. It's
Sure.
it's a cool camera. It's a SWO ASI. What's the number? 194 or something like that.
There's
So I was
294.
kind of surprised. 294. That's it.
Okay. The 294 has a slightly different, so compared to the 183, which has this characteristic, pretty much all the 183s have this exact shape. The 294, I think it has a slightly different shape when it comes to it. But the easiest way to do that is
10 seconds. 10 seconds.
Okay. So the easiest way to figure out what's wrong with the image and what's wrong with the camera, quote unquote, is to just, take shots like dark images. So the best way to figure it out is just do that. Just do dark images, 5 seconds, 10 seconds, 30 seconds, 1 minute, 5 minutes, 50 minutes, wherever you see the problem, just isolate away the camera, put a cap on it, and take a bunch of dark shots and see if you can reproduce it. See if you can reproduce it with different, port settings and things like that.
Right. Oh, this is a 294. I'd forgotten, but here's the box.
I can see it, but I believe you. So, but okay, just to make life complicated, there's actually two versions of 294. There's a regular one and there's a pro version, and they made a different approach when it comes to the sensor and the firmware and stuff. So there's a lot of things to double check.
Yeah, 294 MC Pro.
Okay, so that's then the newer one. Okay, we can talk about that a little bit later. I still have some stuff to share with you. So, okay, let's actually talk about the actual. So we have covered the technology basics, and what last chance to ask some more questions about the technology basics if anyone wants to.
Yeah, I also have a cooled camera, the ZWO 183, which I think is similar to what you have.
Yeah.
But I've been noticing recently that I'll tell it I want it to go down to a certain temperature, and it'll never get there. It'll get to some low temperature with the power will be 100%, but it can never get to where I want it to go. Have you ever run into that with yours?
So what I'm thinking might be your problem is the power supply that you're using.
Okay.
You just don't have enough juice in your power supply to push it as hard. I have had a different problem. I just simply forgot to turn on the 12-volt power supply, and it would start cooling, and at some point in time it would say, hey, I just can't do it because there's something wrong here. So I look at it and I see, okay, yeah, the USB connection worked, the digital part works, but the actual cooling doesn't work. But my bet is on the not enough power. So you should probably have something that can give you 12 volt, probably 8 to 10 amps on the power supply.
I mean, it's the power supply that came with the camera, so I would think it would be adequate for it. But
what software?
Well, it's the ZWO software that I control it with.
Oh, okay. I have seen any similar issue with SharpCap. It was just not pushing the camera hard enough, and occasionally a firmware or a software update could fix these problems. But again, without actually looking into the individual case, I really can't tell. Okay. I'm using the QHY version of the 183, and I have not had an issue pushing the camera to cool it down. Really, I mean, even in the summer, it would easily go down to -15 Celsius, which is, definitely 30 degrees below ambient easily.
Okay.
Hey George, I just want to ask something to his. I have the 183, and I found that SharpCap works a whole lot better than the actual ZWO program that it came with.
Oh, okay. Well, I'll give that a try.
Yeah, because I set mine at I think it was like negative 14 Celsius, just trying it in the house, and it went right to it and shut down. And then when it got hot, it came right back on.
Mhm.
But
Okay.
I just recommend Sharp Cap with that one.
Okay.
Hey, Don, I'm just curious. Are you by any chance operating at a high frame rate? Because if you did that, the element would generate a lot more heat, and the Peltier would have to work harder.
No, I don't think I'm doing anything unusual in that way.
Remember those, they're always a delta. So that's why George keeps saying from ambient. So it's, as David said, it's based on the heat coming off the device minus its capability. So yeah, if you add more power, you can, but there's also just a maximum limit. You could say go to negative 200 C and you're never going to get there, right? Because it's a delta number. So where were you doing this? Were you doing this indoors at a warmer or outside when it was cold? Right. So it's always,
I've tried it both places, and I'd tell it to go to 0 degrees or something, and it would get to 5 or 6 and stop. It wouldn't get.
so what you want to do is write down, you could probably just manually plot what your ambient temperature is. And if you had a temperature probe to be able to see the actual camera temperature to where it got to, you can see what your delta change is. And changing your power supply or the other software that they were saying, you can see what your deltas are again. But it's always about a delta change on those, not an absolute temperature.
Okay.
I hate to say it, but if you cannot get it below 5 Celsius, positive 5 Celsius in an ambient of your room temperatures, then two options: something is wrong with the power supply, or worst case, something is wrong with the actual camera itself.
Yeah.
I had some problems with N.I.N.A, the other software that I use, when the camera software was not up to date. It just did not have the latest libraries from QHY, and it just did not work properly. When I updated the software, that worked really nicely. So I'll get to that point in a minute. Let's just move on, just in the interest of the time. Excuse me 1 second. Okay, sorry about that. Just my throat got suddenly dry. Okay, so when it comes to actual imaging and gathering the information before we even start processing it, let's just cover the basics. So what kind of frames we deal with? So light frame is basically the frame, the image that contains the object that the useful information, right? The dark images, the darks, they are basically the ones that are they're capturing the thermal noise of your camera, and they are going to be subtracted from the light itself. The bias mostly is used for the older DSLR cameras. I haven't seen use with my Sony 6300, neither did I had any benefit from them on the 183 camera. Your camera might need it, but most of the newer cameras don't need it. It deals with the readout noise of the camera. Basically, you take these as very high speed, so you don't build up any thermal noise, basically the same things that the darks are dealing with, but they are actually capturing some extra part of the noise that you also subtract. In addition to these three types of images, there are flats and dark flats. So the flat images, they're dealing with the optical imperfection of your optical train, of your telescope, of your lens, and so on. And I think I can show you some examples of it. Basically, unless you have a $10, $20, $30,000, telescope, there's a good chance that there's a curvature in your field of view. So the corners of your sensor are not going to be as bright as the center of the center of the sensor, and the flats are basically just adjusting for that kind of imperfections. The dark flats are being basically the same function as the regular darks, but they are dealing with the length of time, the imaging time that was used to capture the flats. So just for example, for my setup, when I'm imaging regular objects, I use 3 to 5 minute exposure times, and the darks are matching with that. For flats, I usually take about 600 millisecond images. That's good enough for my sensor. And I take also darks, basically just cover the telescope at the same time as I took the flats, and just do dark images about 600 milliseconds. JPEG and RAW images are usually coming from a DSLR cameras, versus most of the astro cameras, they use a FIT format that's used by NASA, ESA, all these astro agencies, and they're generally used for scientific purposes. Now, when it comes to dark library, what's a dark library? So the dark library is basically just a collection of images without any information. They're capturing the thermal noise of your camera. So what I did is, and that's how I see people doing it also, that I have basically a structure of folder where I use the software that I'm using for imaging, and for different gain and offset settings, I have different exposure times. What's the benefit of this? If you have a thermally cooled camera, so a Peltier cooled camera, you can set up the temperature of your camera even at daytime to the certain temperature that you want to do the imaging. In my case, I use the -10 Celsius and the -15 Celsius. I have not seen much benefit below 15 Celsius, -15 Celsius. So it should be good enough for majority of the imaging. I did see some people actually go down to -20, -30. It's just using a lot more juice for a very, very minimal return. The consideration that you need to keep in mind is, if you're doing these dark libraries, if you're doing it for a regular non-cooled camera, you actually have to take the darks at the same temperature as the light images. The simplest way, just do it at the end of your imaging session, because there's a good chance that it's going to be, the ambient temperature is going to be similar. Of course, if through the night the temperature drops from 70 to 40, well, it's not ideal condition, but it's still okay to take those images, although it's going to be lower temperature. With the cool camera, as I mentioned, because you control the temperature, you can actually set it up, put it in a closet, and let it shoot all of these images ahead of time. So you can spend the time in the night actually doing more imaging, or you can go to bed earlier. One thing that I learned is definitely you want to use the same app to create your library that you use for imaging. So if you are using SharkCap for imaging, use SharkCap for the dark library. I have actually both SharkCap and N.I.N.A for all of these values that I use. I rarely go past 300 seconds, very simply because of tracking, second, all kinds of objects in the sky. So if I have to toss out a frame, it's 5 minutes of my imaging time versus much longer time. And with the light pollution in my backyard, anything past 5 minute exposure, it becomes like too bright, even with the light pollution filter. Any question here?
I have a quick question about flats.
Mm-hmm.
I don't know if you said what you used to create them. The joke was people always used old T-shirts or clean T-shirts. What do you recommend for the?
I just use an LED
image
tracing
field?
board. I just use an LED tracing board, and I just put a couple of sheets of paper to dim it down. That's all.
Okay.
T-shirt works just fine. Something to, as long as you can control the brightness, it's fine. It doesn't have to be an absolute value for the brightness. It just needs to show you the curvature. That's all it cares. I'll show you. Just remind me, and I'll show you some flat frames that I have. All right. Okay. So basically, how is my imaging evening look like? So I do the basic setup, do a rough photo alignment, do the cabling. When it comes to rough photo alignment, use your cell phone, use a compass, whatever, just get it close as you can to Polaris. As it gets darker, I start cooling the camera, let it cool down, and I usually use 10-15 minutes cooling time to avoid the thermal shock on the camera. While that's running, I play with the polar alignment, usually with the pole master, get it going within a few minutes. Then I use the N.I.N.A or a drift alignment method to get it going. You know, to do the to fine tune the polar alignment. Then I do the multi-star alignment just to kind of get the mountain idea of where it is in the sky. Since I'm using a Skywatcher mount, I'm using extensively the EQ mod software, and it's a really nice star map that you can build with it. When I'm ready to start doing some imaging, then I pick a target in Stellarium or in target part of N.I.N.A. Lately, I'm using N.I.N.A a lot more. It's just such a nice software. I'll show you that in a minute. And when I'm ready, I set up and say, okay, I need 10 images of this length, and let N.I.N.A do the magic. When I'm done with the imaging session, when I'm done with the gathering of the actual object data, and I can go across multiple objects, but the main thing is before I tear down my setup, I always capture the flats and dark flats. It takes, since each of these images are 1-2 seconds max, right? Then capturing like 20-30 flats, it's easy, a couple of minutes worth of time, but it's going to be a great help when it comes to calibrating the the images after stacking. When it comes to my processing flow, I just do a simple raw review of all the images, making sure that there are no major problems like somebody walks over with a flashlight and messes up your image, or an airplane comes into the picture. We are in the Knoxville area, we have an airport, so things happen. Then I usually load up all the images that I have, light, dark, flat, and dark flats in Deep Sky Stacker, do a quick super pixel mode. And what that super pixel mode does is basically combines the red, green, and blue pixels into one pixel. And because it combines 4 pixels into one, it drops the image resolution, so my processing gets a lot faster. So I can get my rough, look on things, how the data is. When I'm ready to when I see all the data, I pick a reference image, and when I'm ready to do the final full stacking at the high resolution, then I say, okay, this is my reference image, and we'll talk about the reference image in a minute, and just let it run through its paces and just walk away, go for lunch or whatever the next day. It takes usually 20-30 minutes to get the stacking going through the whole setup of everything. When the stacking has been completed, I pull the raw image into Serial, do some tweaks in it, then do the final tweaks in Darktable. So let's just kind of walk through this process. So here's basically the one software that I'm using, which is SharpCap. I usually use the SharpCap for more interactive approach. What do I mean with that? So SharpCap can be used for all kinds of imaging, but I think its strength is actually planetary imaging. It's a very simple point, click, get the images going, and that's it type of imaging. You'll see how much more complex N.I.N.A is and how much more powerful N.I.N.A is. So what I use this for is usually for actually using it as a crosshair when I'm doing all the star mapping. Where is each the 3-point star alignment, just to center the stars and things like that. And you can reduce the time of the exposure here to literally to a couple of milliseconds. When it comes to the question about those extra artifacts, this is the settings that I was talking about, the DDR buffer on. So you can turn it on and off in SharpCap. And that way you tell it, okay, you don't store the data in local cache. You need to send it over to via USB to my laptop, or you can keep it locally. So you might want to play with this setting with SharpCap to confirm your problem with the USB port. The next software that I'm using for imaging, which is actually the real imaging, is basically N.I.N.A, this nighttime imaging in astronomy. The nice thing about it is it knows a bunch of cameras. So it has its own native libraries to control the camera. And here, for example, what I can do when I start imaging, I can actually set it. I want the target temperature to be -15 Celsius and go reach that point within 5 minutes. And you see this graph below here. This is what the camera cooling does. And as you can see, as it starts kind of slowly, slow pulses, it kind of make longer and stronger pulses. The camera, the chip temperature drops. I actually took this picture in my room 2 days ago. So in the middle of the day, at my room is usually 72 Fahrenheit, it goes easily below 0 Celsius, which would be 32 Fahrenheit. So I think you should be able to get it done. Same story when it comes to warming. To avoid the sudden shock on the sensor and the big change in the temperature, you can also set up the time that you want it to warm up. The curve is going to be slightly different. It's going to go in the other direction, but it's going to gradually warm up the sensor to a room temperature. So when it comes to imaging, there are a couple of things you can do in N.I.N.A. The first thing you can do, just simply go here, type in the target and the positions, and you can say, okay, I want X amount of images. This is my length. This is the type of the image that I want it to be, and just click play. And wherever the object is going to start shooting. The little bit more complex approach would be going the framing assistant here, and then you can pick an object you go actually, my bad. You go actually first into the Sky Atlas and you pick your object, and then you can send it to the sequencer or you can send it to the framing object, and we can look into the examples later. But basically what I usually do, I go just there and say, okay, in the Sky Atlas, I want to image, I don't know, M42, send it to the sequencer. I say, okay, whenever I'm ready, start the guiding, slew me to the target. It's actually the other way around. So slew to the target first, start the guiding. But before you do all of that, center the target. And in the settings, there's actually a centering tolerance, and I have it to 1/4 of an arc minute set. And basically what it does, if I want to do something in between imaging, let's say I want to move to a star, to refocus, come back, do another imaging and things like that, or perhaps my mount is not as good, I can actually say I want to do 10 images here, another 10 images here, and in between do a recenter of the target. And basically is going to use plate solving. In the background is going to use the same AFSTAP software that we spoke a few minutes back, and is going to get it probably within 20 pixels error in between the sessions. So it's not going to be perfectly aligned down to a pixel, but it's not going to be super bad either. It's a pretty useful software. Okay, let me see what's the next here. So I just, this is basically how it looks like menu images. Again, I was just doing this in my room 2 days ago, just to give you an example. I was just kind of shooting darks here. This is how the imaging screen looks like, but you can move all of these things. It's pretty flexible software. Maybe some other time when I learn this software a little bit more, I can share more information with you. But at this time, I think this is as far as I can go when it comes to functionality. So let me move on. Okay, stacking. So why do we do it? We do it because it helps us get us more details out of the image, instead of having one exposure of 1 hour and then it's question what is going to happen, will it work even? You have smaller exposure times, but you have more images, and then you combine these images and you basically see that the single image is not even close to what we did with the stacking. So how this, and this is an old slide, there's actually a newer version of the software. basically what this software does is this Sky Stacker, you load up the picture files, you load up the dark files, the flood files, and so on. And you can see the light, the object type here in this column. And it's going to first analyze and score your images. And you can click in each of the picture and look through this. And what you need to do is you need to pick a reference image. This reference image is going to basically tell you, or not you, but the software is going to tell it, use this image as a base for all of your calculation and adjust all the images according to this one. You can do this two ways. You can go with the highest score, meaning this is my highest quality picture and reference everything according to that one, or it depends what I'm imaging, what I'm doing. Sometimes I pick the middle value of between the best and the worst. If my alignment is not perfect, if my mount is drifting, then usually what I do is I pick the middle path, so I have a little bit of stacking artifact on both sides of the image, so I can crop it out evenly. If I would go with the highest image, all my stacking would kind of slide slowly into one direction and my object might not stay in the middle. So it depends. Okay, the next slide. So after the stacking, the picture is not going to be as bright, but very easily by adjusting the curve, you can get out all the details. So let's just talk about a complex setup when it comes complex stacking cases when it comes to Deep Sky Stacker. Two cases that I ran across was multi-session stacking, which means that I had data from two different nights taken from two different locations, and I wanted to combine them. What you need to do, I'm going to just go back in this picture where you have the list of the images. If you take a look at the bottom of the screen, like bottom left-hand side of the screen, I kind of highlighted it. There's this main group. This is where it would go your first night of images. The second you click on the next tab, group 1, there's going to open a new pan where you can put your second night of imaging. And then once you do that, there's going to be another tab popping up and so on. So you can actually combine multiple nights of imaging. Of course, you have to have different copies of everything in order this to work in Deep Sky Stacker. I know some people using different kind of software, but Deep Sky Stacker is free. So I'm willing to make multiple copies of my darks just to, that's the way how this software works. So you just kind of need to deal with it. I tried to pull in the same dark images and it didn't let me. I had to copy it, but then I realized that, okay, what it does, if I have one set of dark images, then it's going to use it for everything. You cannot specify the same files for 2 different days. So you just kind of have to deal A, copy the files, or B, just say, okay, if this is a dark frame, I'm okay because it's a temperature controlled camera. It's okay to use the same dark frame for all the images. And the second situation that I run across was the RGB mono stacking. With that, I have to actually do this. I have to pick one reference frame out of all of my images and then do stacking separately for each color. So I'll show you an example in a minute. Basically what I did, I looked through all of my images, found the image that I wanted to use as a reference image, and then I said, okay, I want all the luminance stacked together in one image using this reference file that I picked. Then I loaded up and processed all that images, did the basic stacking, didn't do much more than that, but just stacked everything, got everything together, did the dark subtraction, did the flat correction, and all that stuff. Once I did that, I had to rinse and repeat, do the same thing for the red color, do the same thing for the green color, do the same thing for the blue color. So pick a reference image, load up all the files, process that color, save it, put it aside. So that's how could I get around this limitation of Deep Sky Stacker. Okay, let's just quickly jump. We are fairly close to the end. I want to stay as close to the time as possible. So now that I had all these basic components, in this case, I'm going to use the LRGB compose to create a color image out of the 4 black and white images. So this is a very simple option in Serial. You just literally click on this button here, image processing, and there is at the last option, it says image compose. And you just click on each of these buttons and you just load up your frame and say, okay, the luminance, use the L, the red, green, and blue. And when you're done, you say compose. Now, you can choose different options for composing. There are a couple of them. I think there are 3. This is the simplest one. I think it's hue, saturation, luminance option that as the HSL stands for. And you can see that my imaging was not really that perfect because you can see that the colors are not really fully lined up. It's not a big deal. We're going to crop that out later. But you can see that in this particular case, instead of the green, my picture is actually blue. So what happened is this was imaged across one night. I was up till about 4 in the morning and the moon came out while I was imaging the blue. So the blue information actually kind of became a lot brighter. No big deal. We're gonna calibrate that out in a second. This software also has a very, very powerful color calibration option. There are 2 ways to approach it. One is use just a regular color calibration where you pick a star and you pick a dark area and say, okay, use this and find me the values. Or the other one is a little bit more intelligent. You actually tell it, okay, this is the object that's on the picture, and find in the database how that object is supposed to look like. So it's going to color correct it, and on the back end, it's not visible, but on the back end, it actually tells you what values have to do to pull it out. So it's going to do the color correction according to some serious measurement, and this is how most likely this object looks like. It's not as bright, it's a little bit dim. So let's see what can we do to deal with that image. So what happened is, in this software, you can actually at the bottom tell it how you want the image to be stretched. In this case, I did the auto stretch, just I wanted to see the imperfections of my system. And you can see that the object is actually very bright, but in the corners, you have these extra imperfections, and you can see that it's actually kind of the corners are actually darker. This is where the flats come handy, and at that time I did not take flats because I just wanted to test out my mono camera. So we have something called background extraction, and what it does, it sets up these control points, and you can remove these extra points that you don't want too close to the object, and it's going to use an algorithm, and it's going to actually even out and remove that noise. That looks pretty nice. You can see that the unevenness actually went away. We still have some artifacts, and if you take a look on this corner here, you can see that this is kind of that sharp star shape that we actually had in the dark frames, right? What happens here is I actually, while I was imaging all of this to the different colors in the time, I had to do a meridian flip. So half of my images were imaged on one side of the meridian, the other half was on the other side of the meridian. So when the dark subtraction happened, the image was 180 degrees, and I did not compensate. I did not pay attention to it. So I need to redo the calibration of the darks individually, but it's not a big deal. It's still, you can, calibrate it out. So if I do the actual histogram transformation, because that previous image, it's actually an auto stretch. So it's going to pull it out all the way to the maximum as much as it can. But when you put it back to the normal visible value, now you can actually see that my histogram and my image actually looks much more natural than the other one. It's actually more where it needs to be. And once I got out from Serial, I actually saved that file and I loaded it into a Photoshop-like software called Darktable. And then I actually do the final image processing. And you can see this is where I started. This is where I ended up with. So pulled more detail out, added more color. It's probably at this time it's leaning to a yellowish picture, but you know, this is part where your artistic side is actually critical more than your scientific side. And at the end of the day, this is how my picture actually ended up being. And here's the list of software that I use and I use so far. So I'm going to leave it here if you want to take a picture or a screenshot, just in case you want it. And as this is basically where my presentation ends. If you have any questions, feel free to ask, because the next slide would be the question and answers.
Yeah, I was going to say, George, I did a quick look. N.I.N.A, I hadn't seen it before, but that's because I'm not a Windows person. Do you know if any of these will run on other operating systems? I know Serial I use in Linux. N.I.N.A is
Serial,
Linux.
yeah, it's Linux. Darktable runs on Linux. GIMP runs on Linux. I actually know that these three, they definitely run on multiple platforms. N.I.N.A is not.
That's
It's
.NET, so that's Windows only. Yeah.
Yeah, this is Windows only because it's heavily ASCOM based. So anything that's ASCOM, it's equals to Windows.
Yeah. The other question I had on N.I.N.A was, do you have to be network connected to the plate solving, or does it do the plate solving locally?
So you would set up ASTAP to do a local plate solving, so no network needed. You have actually options which plate solver you. So yeah. Thank you. That would be it. If you want, I can fire up N.I.N.A and we can play with it. And if you give me a second, I'm going to just quickly power on my camera. It's plugged in. I just don't run the cooler, just to avoid the extra fan noise.
Hey, George, while you're doing that, I think
Yeah.
given the fact that we got kind of glitchy when we started and that the program's a little longer, we might, with thinking about for Rob also, for the Astrotech, and for the astrophotography discussion, maybe what we should do is go ahead and ask you some questions, but the Astrotech and the follow-on astrophotography, we do it a different night. And
Yeah, we can. Yeah, we can do that.
and I hope you can come. And I want to ask the rest of you, you want to try it tomorrow night, Thursday night, or do you want to try it next Wednesday as a special continuation? Anybody got any comments?
Yeah, I know I wouldn't be able to do the next couple of days, but next Wednesday is better for me.
Okay.
Yeah, I like next Wednesday better.
Yeah, I think so. Either way is okay with me. The other thing we could do is, that's probably better. We don't want to continue into to March because we've already got a speaker for March. So
wouldn't it be, the questions be more fresh in minds if we did it like tomorrow night when the weather's so bad nobody can go anywhere anyway?
Oh yeah, but Rob Scott can't do it tomorrow night, and he's not only heavily involved in astrophotography, but he's also our astrotech. So that's.
I don't know either if I could do it tomorrow night because
okay, George.
I need to talk to some Indian folks for my team. So they are 12 hours ahead. So this is the time where I would kind of talk to them.
Yeah, but let's go ahead tonight for at least for a few more minutes, and while it's on our minds, and this is a great program, and I hit George with a few more questions. So George, it's fantastic, and I thank you. So.
No problem at all. I hope I haven't confused you that much, and you know, it's a lot of information to digest, I know, and I try to keep it as short per topic as I could. I just kind of had to go through this to bring you to this process so you would understand why I do things the way I do things.
It's very, very impressive, and so great. It's more than an introduction. Great run through. So we'll get back. Maybe 15 minutes of questions or something like that is about right. If that's okay for everybody. I think we'll do it. We'll try to get back into it next Wednesday. Okay.
Okay. If anybody has any questions, yeah, feel free. You can always reach me on Facebook or send me an email if you have questions. I'm fairly easily reachable. I'm going to just kind of, in the meantime, I have N.I.N.A here, so I'm going to just let me stop sharing this guy here in the background and fire it up. So let me just quickly do a refresh. So it has all of these cameras that you can load up, and it's actually, it can talk to a Nikon camera. It has drivers, but in this case, I'm going to use my color camera and power it on. And right now, it doesn't know where it is. So it's still measuring the chip temperature because it just connected. So let's just give it a minute until it measures things. And you can see that it's not doing any cooling at the moment. So it's just showing me the graph
George, I
here.
have a question. I don't know
Yes,
if
sir.
the rest of you are seeing or not. What I'm still seeing, maybe my screen's not updating. I'm still seeing soft.
Oh, I see. Yep, it says my screen is paused for some reason. Yeah, hold on 1 second. Let me stop sharing, start this.
Thank you.
Yeah, let me. Yeah, this is something again. I'm used to my work. Okay, so there you go. It should now show.
Thank you.
Okay, I'm used to my work where it actually, I always share my whole desktop, but in this case, I just have to share the application. Okay, cool. So you basically see in this corner here that it's measuring the, come on it. So it's measuring the temperature. Okay, hold on 1 second. This annotation page is not playing nicely. There we go. So it's actually measuring the ambient temperature here in my room. If I actually say it, I want to go to -10 degrees and say, okay, I want to go through 0 minute, it's going to just start cooling at maximum capacity, and then it's going to go down rather quickly. But I'm not going to do that. It's not good for a camera. So what I usually do, I say 10 minutes. Let's say 10 minutes. And then you're going to see, I'm just going to do 10 minutes here too. If you hit this cooling button, you're going to see it's going to kind of start spiking up a little bit, but then it's going to slowly, gradually start dropping the temperature. And you can see in the corner down here, you can actually see here's how the cooling actually works, and you can see the temperature of the sensor slowly dropping down.
Oh wow, that's cool.
It's a nice little software. I can tell you that. Okay, so while that runs, let me just quickly show you a couple other things. I can actually, okay, hold on, I don't want to annotate. So I can actually connect a filter wheel, I can connect a focuser or rotator, a telescope. This is where my telescope goes in, and I don't have it configured. Actually, I do. So I could connect to it, but I don't have it up here in my room. So that would be connected to the telescope. I can control the telescope. This is where my PhD guiding would go in, and it can control a couple more things. The Sky Atlas, this is where it sounds really interesting. M42, and it's going to say, okay, here's my M42, here's when it comes up, and at this point in time, which is about now, it's actually at the highest point. I'm sorry, we are past that highest point. So, okay, maybe I did not set up the GPS coordinates properly. So anyway, when I'm ready, I can say, okay, I want to slew to it. I want to set the framing assistant, or I can say, send it for a simple sequencer. So simple sequencer would be basically the screen that we were looking at before. And I can just say, okay, I want start guiding, slew to the target, make sure that it's centered. And I want to have, let's say 10 images. And then I want each image to be, let's say 30 seconds. And then I just fire off and say, okay, start sequencing. The nicer option is, for example, in my case, I'm going to send it to a framing assistant. And in this case, here we go, the beginning of left. You can see that my sensor covers only the center of the Orion Nebula. And what I can do here is I can actually say, okay, I want to do a mosaic, and I can rotate this, and I can say, okay, this is how I want it to image. And now I can actually, let me just go back to the sequence and clean this up for a second. Go to the framing assistance, and I can say, okay, Now this is how I wanted it to look like. Add it as a target to the sequencer and just go a simple sequence. And what you can see that now it actually has multiple targets, and I can say for each part of the panel how many images I want. And it just goes through and it would cycle through all of these objects and image it, and then I can actually stitch it together in my post-processing. So, and then I would see the images here in this section. I don't have anything running right now, so I'm not going to do that. I'm going to go back and cancel the heating for a reason that I want to just go on with the processing. And you can see this is the graph. So you can see that it's actually set to -10 and it's slowly dropping from 17. Now it's at 8 Celsius. It's going to keep dropping. So 1 degree per minute, roughly 1 Celsius per minute. And you can see how it's going. So I'm going to cancel this because I don't want it to cool and then you're not doing any imaging. Okay. What else do you guys want me to show you?
I had a simple question.
Go ahead.
Was it somebody else is talking?
Go ahead. I had a question, but you've.
This is a real short one. You showed a program that was calculating the amount of error and then predicting that so that the mount would stay closer in alignment.
Yeah.
I couldn't remember the name of the program, but what I was trying to figure out was, is that a separate thing or is that a sub feature of one of the other programs?
So no, the periodic error correction, it depends on your mount. So you have to have some software that knows about your mount. Okay. What I was using is the EQ mod has this PEC record software. And in the EQ mod that I was using, it's part of that software that basically is specifically built for Skywatcher things. Celestron has its own similar software. I don't remember what that exactly is, but they have their own similar software.
Thank you.
What you can do, I know that some of the cameras actually have the ST4 connection, so which is not the pulse guiding, but the kind of the old type of technology, and you can actually send the impulses as in the ST4 form to the mount, and it can record it. But you need to check the manual of your mount how to record a permanent periodic error correction. It took me a little bit to figure it out, not a little bit, couple of weeks reading and learning before I got my first usable PEC curve. And literally earlier today, I watched a video and I saw, okay, I'm not doing this really correctly. So I had to go and redo a couple of things because there's a better way of doing it.
Rob, thanks for telling us that. I had this idea you worked this out in a couple of nights, a couple of evenings, and I was feeling really, really inadequate. But took you a little more time then.
Yeah, with the EQ6 mount, I'm talking about that because that's what I have. And there are a couple of known things, which is basically what's the cycle of your worm gear, which is about 8 minutes. So you need to run 7 to 9 cycles, so about an hour. So there's a lot of knowledge out there regarding that particular mount. So I'm more versed on that mount than on, for example, Celestron. But Google your mount, see what the manual says, see what people on Cloudy Night forum says about that mount and the periodic error correction. I know definitely that Celestron does have a way to record the PEC, and there are softwares to do that. I just don't know from the top of my head what they are.
Yeah, Celestron has something called the CWPI software that I've used.
Yes.
And you can record it. It takes, when I did it, it took about 10 minutes of recording to get it.
Oh, wow, that's fast. That would be just one cycle
you just start
mode.
guiding and you turn on the periodic error recording and it goes however long it thinks it needs to. And The time I did it was about 10 minutes.
Okay, that's good to know. Yeah, I have played with the CPWI software. I liked it, but the best usage of that particular software if you have the StarSense camera with it. It recognizes it, it works fantastic.
Yeah, I have the StarSense also.
Yeah, if you have the StarSense, it works really nicely.
Yeah.
Did you have any other question?
Well, I was wondering, at least the way I do the imaging, I use the ZWO software, and so you can set the exposure time and the gain. And I usually try to set it so I can see some stars, but I don't really overexpose things because I know I'm going to be stacking. So it's a question of how you trade off how bright you should get each image in the stack.
Okay, so there are two things. Just give me 1 second. Let me find that dude. Okay. There's this little part says optimal exposure calculator in N.I.N.A. And then in SharpCap, there's actually another one. I just can't share that one too. Let me stop sharing this guy, but should be able to. Let me see, where is this guy? Astronomy, SharpCap. Let me disconnect the camera so we can quickly connect to it on the other software. Ricky, you will have to help me with this one. I don't remember where that option is. So let me start sharing the screen now again. Hold on, where are you? Where are you, dude? Okay, SharpCap. Okay, so here is SharpCap. Can you guys see it? Yeah, okay, good. And right now, it's connected to my camera, cameras QHY. And there is, where is that little option? Hold on a second. Oh, there's an option, tools. Yeah, you have to do the sensor analysis. And then when you do, okay, yeah, when you do the sensor analysis, there is actually, there's going to be an option that actually going to tell you, you need to point the telescope to a dark part of the sky where you kind of want to image, and it's going to figure out for you, okay, if you do such and such exposure, the background noise is not going to be that bad, and so on. So there are some tools how you can actually figure it out. I learned from practical example. In my backyard, anything past 3 minutes is just too bright. Definitely depends on your object that you're going to be imaging. A good starting point typically is unity gain setup. What the unity gain is, if you look into the sensitivity curve of your camera, there's a point in that curve where one photon on your photosensitive element is going to cause a change in the value when you do the readout. So for example, if your camera is at the moment in pitch dark and the information from a photosensitive part of the sensor is 0, when it gets hit by a 1 photon, it's going to flip that value from a 0 to 1. That's unity gain. But the problem with the unity gain is that for very, very bright objects, you can quickly blow out the stars, right? It becomes a big white blob. So what you do, you reduce your gain. So you need to have a couple of photons hit that sensor to produce that value of 1, right? So that's where you need to play. So as I mentioned, it's a good start with the unity gain, and then you can go up or down when it comes to the gain based on your object. You need to take a couple of trial shots and see where your star is, where are they blown out, where is the min value, max value, and things like that. And this, or you can, as I mentioned, or you can use these calculators from the software itself. I don't know if I have it. I don't have a license installed on this SharkCap, so I might not even have it as an option. I just installed SharkCap last night to capture a couple of screenshots.
Okay, George. That's great. Shall we? I wonder if we all can get together next Wednesday. Is this good?
Yeah, let's try. Let's keep in touch. If you guys have any
I
questions,
had something. I had some of the stuff. Yeah.
I'm going to sleep in my room because it's smaller and it's a little warmer than yours. Are you using the heater?
Yeah.
okay. So let's see. If you have any specific questions, shoot me a message and I can do some more research, and then we can go from there. And let's try meeting next week then.
Okay, very good.
Yeah.
Thank you, George.
Hey, no problem.
And we got other things to do for our meeting also, but we'll continue to be. In fact, I think this is the last time. We've done this with you before. Had continued things, so we got pretty much through it tonight, though. It's good. Does anybody else have any final comment?
I'm going to have to watch this again before I'll have questions for the next time.
Yeah.
Thank you, George.
Thank you, George.
Thank you.
No problem. Have a good night.
Good night.
Yeah.